Okay, hi everyone. This is a Wolfram Institute working session trying to figure out some science, or maybe it's mathematics, I'm not sure. We are working on what we are calling infrageometry, attempting to build up a kind of mathematics-like structure around the kinds of things that show up in our physics project, in particular, building up something like geometry from the hypergraphs that represent space in our models. And the kind of usual way of building up kind of things like geometry and then calculus and so on and differential geometry rely on the idea that at a small enough scale, space is just like the way Euclid said it should be. But in our hypergraphs, that's not true. At when you go microscopically enough, you see actual atoms of space and you see this actual hypergraph. And so the question is how one builds up kind of a mathematics-like structure to describe what's happening in that kind of system and how one finds the kinds of constructs that have been discussed in sort of standard geometry and mathematics and makes a correspondence of those with what we see in our hypergraph systems. All right, now Jonathan is going to give his corrected version of my introduction, and then maybe Carlos will give a correction to the correction. Go ahead.
Right. Okay. Yeah. So just to kind of contextualize this a bit. So you'll remember, those of you who watched our previous live stream I just brought up the notebook here that we worked through. We were kind of summarizing the initial insights we had about how to define things like tangent spaces, tangent bundles. The beginnings of essentially defining what it means to sort of equip one of these graphs with a discrete analog of a connection, or an affine connection, and by extension a metric tensor, and those kinds of things. And so the plan for today is to kind of to talk about some stuff that we ended up thinking about in relation to trying to define what it means for functions to be smooth, continuous, differentiable, etc., over these discrete spaces. And in the process, we will, one of the things we kind of found when discussing these things was that the answer to that question in turn gives better insights, or at least a better contextualization of the definition of things like tangent bundles and connections. So
Let me try and see if I remember how this works. So I mean,
yeah,
in this concept of a tangent bundle here is we've got from a given node, we have edges that go in a certain direction, in quotes direction, to another particular node. And then as
yes.
I understood it, there's the question of how do you continue from that node? And that's related to this kind of that's related to the connection. If I'm remembering, I'm afraid it's been a month or two since we did this, so
Yeah,
I
exactly. So that was kind of the old idea, and that's mostly preserved in our new way of thinking about things, with one key proviso, which is that these sort of things that we're describing as vectors are no longer pointing to nodes; they are pointing to in some sense, they're pointing to edges in a way that will hopefully become clear in a moment. And so I think I don't know whose phrase this was. I'm going to assume it was Carlos's. This thing that we're calling the edges as places philosophy. But so that was something that came out of trying to think about what it would mean for a function to be smooth or differentiable. And so
can
yeah,
you recap the tangent bundle idea from last time?
yeah.
What is a tangent bundle?
So for so the yeah, in the last live stream we talked about, so you can take all of the outgoing edges from a vertex, and that gives us some analog of a tangent space, right? Some discrete tangent. Each one of these we can treat as being a tangent vector. Each one of these red edges. So then if we look at all the tangent spaces for one for each vertex, we can take a disjoint union of them, and that gives us a discrete tangent bundle. And then
I
we can
see,
take a
right.
global section of that tangent bundle by just essentially applying a choice function, by just selecting a single tangent vector for each element of in the disjoint union, for each space in the bundle, and that gives us a vector field. And so then, but then if we, if we were to choose a pair of vectors for each for each tangent space in the bundle, we would then get a rank 2 tensor field and so on.
Right.
So this would be so this is a global section through that tangent bundle, which therefore gives us a vector space.
Okay.
A vector field, sorry.
Okay.
Right, but yes, so it was this idea partially came out of trying to resolve this confusion about what it means to have kind of path continuity, right? If you've got how do we define the analogs of things like parallel transport? If you set off in this particular direction, in the direction indicated by
what
this
does it mean
tangent,
to keep going?
Right, exactly. So the resolution to that, and I should clarify, I'm going to be talking about the understanding of this as it was maybe a week or two ago. I understand that Carlos and Uti and Nick and people have made a bit of progress since then, so I may say things that are a bit out of date. Please, you guys, interrupt me if I do. But so this is essentially the idea. So if we,
by the way, was Nick going to join us? Is he here?
Nick was not here as far as I could see. He was sent the invite.
Somebody might remind him.
Yes.
Okay. Okay. So.
But yeah. Okay.
It's a weird time of day for him. Okay. Go ahead.
Let's start with a graph. And so the new idea is, okay. So let me contextualize this by talking about the question we were initially trying to answer. So if you take this graph and we assign let's assign a scalar field to it. So if I take okay, so that's some, and so I say graph, I don't know, vertex labels, scalar field. Okay, so that's some discrete scalar field that we've defined on the vertices of the graph.
Mm-hmm.
And so the kind of the initial motivating question was, what does it mean to say that this function is continuous or is not continuous if you're working in a fundamentally discrete geometry? And so the first thing that we kind of established or agreed upon was that if you just have the information at the vertices, that's not enough data to determine whether this is a continuous function or not. Because of course we know that you could, if this were a continuous space and you knew the value of this function at 10 points, then you could always define a continuous function that would interpolate between those points.
Yes.
So just knowing the value of the function at the vertices is somehow not enough information. So then the idea was that, okay, when you define a function over this space, you are not just assigning values to the vertices, perhaps you're also assigning values to the edges. And then essentially notions like compatibility, notions like continuity and smoothness become compatibility conditions between the assignment of values to the edges and the assignment of values to the vertices. So if we take a very simple example of that, so let's do, I don't really know the best way to do this. So
what
if
are you trying to do? You're trying to assign a number to every edge?
Yeah. But in particular, what I want to do is let me do this. Let's make that an association. And so then if I just make this the mean scalar field first, scalar field last. Let's do that. Okay, so in this particular case, I've just assigned, I think, to each edge the average of the values of so the value at each edge is just the average of the values of the two incident vertices.
Yep.
So this would be an example. So within the prescription we were discussing, this would be like a maximally smooth function, right? And kind of the intuition is that you can think of the edges as being like limits. So, so in other words, so if we think about this as being a topological space, the average of the concept of an open set would be, you've got a vertex and you've got some outgoing edges, but the outgoing edges are sort of dangling. They don't have, they're not closed with incident vertices. So the values at the edges tell you kind of things about the limit points of that open set. And so in this particular case, this is somehow maximally smooth. And then the idea is, okay, so suppose we didn't want to assign a value of 42 here. We want to assign some different value. The more different that value is from 2 and 82, the kind of somehow the less smooth the function, right? That's the intuition.
Yep.
So as a kind of as a very basic prescription, and no doubt there are more sophisticated ways of doing it than this. But you might say, okay, well, let's take a finite difference between 2 and 82. And if the value assigned to the edge lies within a multiple of is sort of within 1 times that finite difference, then it's a maximally smooth function. If it's 2 times that, if it's within 2 times that finite difference, then it's kind of the next most smooth case, and so on. So in other words, you characterize the kind of the differentiability class of the function by the order of the finite derivative that you would need in order to interpolate between the values of the vertices and edges. And so
okay,
that's
hold on.
Yeah, sorry.
Okay, first point.
Yeah.
Let me try to understand your definition of open sets and so on.
Yes.
So, which we should be writing down some of these definitions, and I am.
Okay, so
an LLM will conveniently summarize this meeting for us, but
open set claim. So
collection of vertices with dangling edges.
Yeah. Okay. So
a closed set, please, is
there are no a collection of vertices with no dangling edges.
Is it a subgraph?
Yeah. So each of these would be subgraphs. Yeah. In fact, let's say that subgraph containing dangling edges. Now, I don't know whether this is
where all edges are dangling.
No, I think the subgraph, the closed set will be a subgraph, as you say, Stephen. I think the open set will be a closed set together with a collection of vertices that are limit, and then those have dangling edges on those.
All right. Okay. Yeah, so closed set.
I think it's probably easiest to say, open set is a subgraph that contains dangling edges. A non-open set is a subgraph that contains no dangling edges.
Okay, but I was thinking that the intuition was this: that a subgraph is just a collection of nodes with the vertices between them, right? And that is more like a closed set, and that the open set, as Carlos has commented, there's kind of, where's the outside? Well, the outside is nodes that are connected to nodes in the subgraph, but you don't see the nodes outside of the ones in the subgraph. Instead, all you see is that dangling edge.
Hang on, wait. So let's be very clear. What do we mean by subgraph? Because I'm using the word subgraph to mean a subset of the a graph defined by a subset of the vertex set and a subset of the edge set.
Yes, I guess that's correct. That's the correct thing to say.
But not any subsets, right?
What?
No, so I think a subgraph could be any subset. So it can
subset. Okay, so you're saying any subset of vertices and edges.
Yeah. So in particular, in order to make this claim work, you need to have the ability to have edges, to have a graph that contains an edge, but whose edge set contains a given edge, but whose vertex set does not contain the endpoints of that edge.
Indeed, absolutely.
So maybe we shouldn't call this a subgraph, right? Maybe we should call it something more, because it's that's right, a slightly
closed. Look, I think there's a notion of a closed set, which is something where maybe what is it graph theoretically? Maybe it's something. Okay, well, it's basically something where that nothing is dangling. You don't miss.
No, but that's a non-open set.
What's the difference in a closed set and a non-open set?
A closed set is one whose complement is an open set.
Right. Okay. All right. So non-open set, no dangling edges. So we deleted. Forget the subgraph claim. I think. I mean, it's just a.
I don't know. We need some kind of we need some kind of word for
that. Is a subgraph. Why wasn't that everybody's?
It's like a monomorphism.
What's that?
I
That's
mean,
not
like,
that. Sorry, please.
no, I was saying it's like a monomorphism.
What is?
Like the subgraph definition you're talking about, I think it coincides with the one that we use in category theory, right? We map the vertices and
Yeah,
the
that's just an injection,
yeah.
as would be any subset. But the whole point is that it's a potentially incompatible collection of vertices and edges.
Yeah.
The traditional definition of a subgraph would mean that would entail that if you have an edge, like in other words, a subgraph still needs to be a valid graph. What we're talking about here is not necessarily a valid graph.
Yeah, it could have an isolated node, for example.
Well,
Yeah.
isolated nodes are okay, but isolated edges are not.
Exactly. Yeah.
So it's not. This is not a graph. It's a collection.
Okay, could we
of
have an edge which has neither of its nodes on it, so to speak?
Yeah.
I don't think that would be necessary for anything.
It's not necessary, but we could in principle, right? And what we're saying is we're
Yeah.
defining a class of objects here that are something like subgraphs, where we are allowing the flexibility of selecting, sort of highlighting a set of vertices and highlighting a set of edges in an independent way. And we are saying it is non-open when all the edges actually correspond to some vertices that have been selected, right?
Yes. Right. Okay. Fine. Generalized subgraph.
So I mean, we can try.
Okay, a dangling edge. Let's define what a dangling edge is. A dangling edge is an edge that lacks either one of its nodes or both its nodes.
Yeah, an edge whose at least one of whose
Nodes is missing. Endpoint
nodes
nodes
is missing from the vertex set of a generalized subgroup.
Right. Now, could both of them be missing?
So I should mention at this point, by the way, that that there's a term for this in the graph theory / string diagram literature, which is open graphs. So for instance, when you have things like circuit diagrams or you have string diagrams, you're allowed to have ports and sort of wires that don't connect up to nodes and things, and those are referred to as open graphs.
Okay.
And
make a note of that fact that a dangling edge is like a port with nothing plugged into it, so to speak.
Yeah, it's the right intuition, absolutely.
Right. Okay. Okay.
So the idea would be, we can say, okay, if we were to select.
Sorry, can I understand a closed set now? So the complement of an open set, I don't understand what that looks like then. The complement of the open set is surely something.
Yeah, so in this particular case, I think in the way that we've defined it, I think you were perhaps I was maybe overly dogmatic. Non-open sets, I think, are closed sets in this case, but they wouldn't be in general topology.
I think that's right in this context, yeah.
And I think in topology, these are called door spaces. Spaces where every set is either open or closed, like a door.
Okay, but hold on. Why is this the claim that the closed set is the complement of an open set? I don't understand. If the closed set has no dangling edges, why is that the complement of an open set? Because the complement, I would assume, is a graph complement, where you're taking the generalized subgraph that is the complement set.
Right. But if this is an open, if I okay, let me try and draw a picture of this. So let's take wait.
That's smaller. I think you only had.
Of course, yeah. Sorry, no, I forgot. There's a not vertex names. There's a
those values. Yeah.
Yeah. Okay. So if I take What's the best way to do this?
What do you want to do? What are you trying to do?
I'm just trying to. I just want to highlight. Hang on, wait. I want to highlight all the outgoing edges, but not the incident vertices. So if I just do undirected edge, 5, hash.
Yep.
And so if I take highlight graph, that. Okay, so then if I do no, wait, I want to do join that with there we go. Okay, so that would be an open set, I think. Right?
Yep.
I agree.
Yes.
Okay, but then so if we remove that, if we take the complement of that, this is closed, right? So if in other words, if I take the so
Fine.
if I
Yeah, you're right. If you remove all the danglers, then nothing dangles.
Right. So if we call that let's call that open set. And I take graph complement of this comma open set. Can I do that? No, this needs to be a graph. Oh no, wait, no, oh no, it's graph difference, wouldn't it be? There we go. Yeah, so that's a closed set with a isolated point in this case, because
cool.
Why is that
All right. Okay. So let me just internalize this for a second. So an open set has dangling pieces. Nice dangling piece picture there. And a closed set removes you remove it, like pulling out the spider, so to speak. I mean, you're pulling out this thing which has dangling legs. And since you pulled out all the dangling legs, there are no dangling legs left. Therefore, the thing is closed in the sense we originally expected.
Right.
Okay.
And so oh, sorry.
I was saying probably just to reiterate so that everyone's on the same page. The vertices that the red edges point to are like the limit points, and so the closed set like includes them. The open set doesn't.
Right, exactly.
Right. Okay.
I'm sorry. So
the incident points that are not contained in this case would be the limit points of this open set, right? Because an alternative definition of an open set is one that doesn't contain its limit points.
Yes, could you write that down? That's a good and important point. So, I mean, the limiting process here, normally, okay, let's talk about how you take a limit, right, in this set.
Well, yeah, so that's why
the answer is you just walk.
Right.
The way you take a limit is you walk on an edge.
Right.
And that's a non-trivial thing, because normally when you take a limit in in continuous spaces, topology, whatever, the process of taking a limit is something much more arbitrary. I'm making sense?
Yeah, that's the whole point, right? So,
right, so can we make a definition, please? A limit.
Well, I mean, the beauty of this is the definition of a limit is the same as it is in analysis, right? It's the open set definition.
I know that, but you can independently define a limit. To take a limit is to walk. I'm a little okay. There's a definition here, right? Because normally it's a very floppy thing to take a limit. In this case, there's a very discrete way that you can take a limit.
Yeah, right. That's the reason for defining it.
I know, but what is the definition of taking a limit, of the process of taking a limit in these graphs? It is you walk one step. Is that true?
Well, so you would take I mean, yeah, the procedure is you look at what vertex bounds a dangling edge. That's the operation of taking a limit.
Yes, I understand.
The dangling edge defines a direction, and therefore
exactly.
Equivalent.
So can we write down? I mean, the basic point is you're taking a limit in a certain direction. The only directions that you can take limits are the directions corresponding to edges. So the taking of a limit is just the walking down an edge to the other end.
I just wrote this. I mean, with more generality.
Well, okay, fine. I was looking for a definition of the process of taking a limit.
Evaluation of a limit is, determination of the vertex that bounds a dangling edge.
On the other end of it. Yeah, okay, fair enough. All right.
Right, but
In a
that's
closed
that's
set, like, probably should be, because in a
Say
closed set,
again?
there are no dangling edges. So it's probably just a walk in a closed set.
Yes, limit in a closed set is just a walk, and everything, and you always you'll always be in the closed set as you
Precisely.
take these limits. This is very nice. I might even
Yeah.
understand open sets now. No,
right.
it's
And so, as I say, this is obviously, once you've got this apparatus, this definition of the limit is just the standard definition of a limit from analysis, right? Which means that we can, things like metric space completion just means doing exactly this process, right? Kind of putting in vertices at the ends of dangling edges.
fine. You say it's just like analysis, but it's much simpler than the case of analysis.
What do you mean?
Well, I mean, you just got the explicit vertex right there. You just put it in. You're not having to worry about, this limit set that's some complicated infinite thing, et cetera, et cetera, et cetera.
But that's just like saying, you've got an open set, you put in its limit point. That's evaluating a limit. It's exactly the same.
Fine. It's clearer for me. Okay. let's keep going.
Right. Okay. So anyway, but so the reason for talking about this is all right. This was by the way, I should mention this was the original intuition that we started off with, right at the beginning of the infrageometry program. So now we have a much more kind of robust reason for making this initial claim.
Yep.
But okay, so then the idea is, okay, so now we have values of the function defined at the edges.
Yep.
And we'll proceed to generalize that a little bit in a moment. But so then the idea
you were describing different kinds of continuity for different. I mean, so you've got a scalar field.
So let's take the example of this edge, right? So right now I've just got this I've got the edge value right in the middle of the two vertex values.
Mm-hmm.
But okay, so the finite difference in this case would be 80.
Mm-hmm.
So one very crude definition, but which actually kind of can take you a reasonable distance of continuity classes or differentiability classes would be to say, okay, so if the value of the edge of this edge lies within distance, lies within 80 of either of the vertices, or maybe perhaps between the midpoint, then it's somehow that's the smoothest possible class. If it lies within distance 160, i.e. 2 times 80 of that, then it's the next smoothest possible class, etc.
Well, I mean,
and so
sorry, the most naive thing is it lies between 2 and 82.
Right.
It's an undirected edge.
What you are essentially, okay, so the idea behind this is, okay, so now we have to, this is one of the places where this edges as places intuition comes from. But so if you imagine, I'll make a picture of this in a moment, but if you imagine there being a kind of a point in the middle of this edge,
mm-hmm.
So, and we want to assign a value of the function at that point.
Yep.
So the idea is, what if we were to construct a polynomial interpolation between the function value at this point and the function value at this point that goes through the value at that point,
mm-hmm.
What degree of polynomial would you need in order to make that work? And so the higher the degree of the polynomial, so in this case, you can do it just with linear interpolation. So the degree of the polynomial is 1.
Mm-hmm.
The higher the degree of the polynomial, the claim is the less smooth the function.
All right, let's make a picture with a manipulator. You just what we've got is we've got 2 anchor points, 2 and 82. Right. We know. Don't mess up your beautiful graph. Keep scroll down.
Okay.
Let's
so
make
do you
section.
manipulate the whole graph, or?
I wasn't thinking you would manipulate the whole graph. I was thinking you would just make a plot of function. I mean, it's a very simple thing here. Just where the end values of the function are 2 and 82, mm-hmm. and you're simply taking, I mean, if you make a manipulate that just has an interpolation of a different interpolation order with the 2 value, some value in the middle, 82.
So okay, I don't know the syntax for interpolation.
Okay, all right. So just say 2 and list inside there. 2 comma x comma 82. Okay. All right. So now say I should call that middle thing, I don't know, m or something. Okay. Call it, instead of x, call it m.
Oh, I see. Okay. Yeah.
And then of x. Okay. Now say plot that.
Yep.
From 0 to 1. And then you're going to manipulate that as a function of m. Okay, now put a manipulate to give a value for m.
And let's do m between 0 and 100 or something. Start off with.
I don't know why it's pink. Why is it pink? Oh, requested.
Order has been reduced to 2.
Maybe it just can't interpolate. Hold on. Let's just look at that interpolation. At 2.
Yeah, I mean, it had that. It was complaining about this even when we constructed the answer. So if I do 2, 10, 82, what does that
Oh,
mean?
I think you need, I mean, you might need interpolating polynomial. There's another function, interpolating polynomial.
Oh, I see. Okay.
Get rid of comma x there and get rid of the x after it.
Nice. Okay. Okay. Cool. Is that the wrong way around? We want it 82, 2?
I don't think
No?
so. I think you want 2, 82, but I don't know what the.
That
Okay,
seems to-
maybe you want the values. Maybe you want in that interpolating polynomial, we want 0, 2, and then a half, m, and then 1, 82. See what I'm saying? You got to have x and y values.
I see. So 0, 2.
A half, m.
Yep.
I think.
Yeah. Okay. Yep. That makes sense. Cool. Okay.
Okay, so now we've got those things pinned at the end. So now there's a question of what's the degree of that interpolating polynomial. So that one was of degree 3, but now what you're claiming is so what are you claiming here?
In this case,
You're claiming
yeah, this is always going to be quadratically
it's always
interpolating.
right. So look up the documentation for interpolating function. Maybe it has a way of having a different order.
But crucially, I mean,
No, I think it just makes the polynomial through that.
Yeah.
Okay, so maybe it isn't the right thing. But go ahead. What were you saying?
Crucially, so in this case, yes. So you for a binary edge, you can always it will be at worst in this case you can make do with a linear interpolation, but it will be at worst a quadratic, right?
Yes.
The point is for hyperedges that's not true, right? For an arity n hyperedge, in general, it will be at worst of order n. So that's kind of that's the least smooth it could be. But if you could make do with a polynomial of less than of a degree less than n, then that function that's somehow a more smooth function than the one where you needed degree n, if that makes sense.
Yep. Yeah. So I mean, the question is, okay, hold on. In that picture you made, okay, but back down to the function.
Yeah.
Okay. So here, for what values of m is it a linear function? Answer, if m is really at the 0.5 point, there's only one function. There's only one linear function.
Right.
I mean, is that true? But it's a piecewise. No, wait a second. There's only one possible value of m for which that thing is linear, which is the average. Okay, so what does that tell us in terms of degrees of continuity and things?
So somehow the more distant this value is from 42, i.e. from the value that would make this linear, the less smooth the function is. But this is somehow, this assignment of values to edges corresponds to the most smooth possible function that you could define given the vertex values that we started from.
I agree. But you can put arbitrary values on those edges if you want to. It just won't be a very smooth function.
Right. And so one of the insights is that, I mean, one of the claims would be that in this infrageometric formalism, there's no such thing as a truly discontinuous function. There are only functions that have, lower and lower degrees of smoothness.
All right, let me understand that claim. That's an interesting claim about what it means to be discontinuous here. I mean, let's use my favorite. Let's use a one-dimensional grid graph, okay? Maybe you can do it at the bottom.
What?
Put it at
No.
the bottom. Put it at the bottom of your notebook. Otherwise, we'll never keep track of what the heck was going on. Okay, grid graph. Okay. So now we do the same jazz for this. Because now we've got something where we've got, this literally is, a function of position. Because there's a canonical labeling of the nodes by position.
Right.
So now what you're saying is, there is no, which is not in a sense totally surprising, there is no discontinuous function here because, you can have a function, we could actually just draw the function, right? Whatever the values are here, we literally can draw the function on top of this graph.
Right.
So there will be functions that will be wigglier and not so wiggly. And so a smooth function might be one where the actual, differences here are small, I guess.
Mhm.
Okay, all right. It was just to help me understand. I think that's a useful, and in terms of this continuity thing, that grid graph is a case where one can already formulate all of what one needs to formulate.
Right. Right.
Okay.
So that, hang on. Okay, let me try and figure out the best way to do this. But okay.
What are you trying to do?
I want to now show a point on each edge because I think that's a useful visualization. So if I
think, Jonathan, I think Nick made a function for this.
Okay.
And I could find basically where he sent it to me, so I can paste it on the Zoom chat.
Okay, sure. If you have a function that does it, that would be good. Can I do graph? Is it graph plot epilogue?
I don't know. I mean, you're trying to actually put those values at those embedding positions.
Yeah. So hang on, wait. If I do edge,
I think you need next function. This is going to get messy. You're going to just draw the thing if it is sort of within the, if it is between, if it has the inequality between those end values, you can draw it as an additional point on the graph. That's what you're going to do, right?
right. Hang on, wait. If I take that, so that's for each edge.
Yep, looks promising.
Yeah. Okay. So actually, I don't even need the edge names, do I? I can just take. So that's can I do epilogue point?
Well, we do point mapped onto edge coordinates.
Yeah. Okay. Yeah. Something. So
you make it the point bigger.
Yeah. So large? No. Oops. Wait. How do I make the point big?
Make point size.
Oh, is that an option?
No, it's not an option to point. It's just it might be, you might be able to put it into the style directive, or you can put it into no point size. Well, whatever. That's fine.
All right. That's roughly what I was trying to do. So yeah, okay. So then the idea is, so now each one of these edges is now an object to which you can assign a value of that function. And in a moment, I'll talk a little bit about how this is one of the cases where hypergraphs become inevitable because there's no reason to terminate this just at the arity2 case. But one of the insights that I think Carlos had was that actually once you start to think of edges as places, this clarifies a lot of the stuff about tangent spaces, because now you can think of a tangent vector not as an arrow pointing from a vertex to a vertex, but as an arrow pointing from a vertex to an edge. And so so you have a natural, the thing you were talking about, in relation to kind of walking along an edge and finding its endpoint, that now becomes precisely the definition of what it means to continue moving in the direction of a tangent vector.
Yes. But so your tangent bundle now, I mean, the tangent vectors at a given point are the dangling edges.
Yes, exactly. Exactly.
And the tangent bundle is then all dangling edges from both directions, because an edge can dangle in two ways.
For a torsion-free space, yeah.
Yes.
Could I clarify something here?
Please.
Yeah, so just on Stephen's point, so basically what happens is you take your graph and then each edge becomes a new vertex, and you essentially generate, you can imagine that you're generating a new graph on top, which is in principle undirected, but then to that graph that has some label of what is a vertex place or what is an edge place, so to speak, to that graph you apply the logic that we applied earlier to the definition of tangent bundle, right? So you basically have an undirected graph as space, and then you do the induced directed graph as the possible directions of that space. And so a tangent bundle becomes the collection of outwards edges, directed edges from any vertex place into all the nearby edge places, right?
Yep. But this graph has two types of nodes. I mean, it's a whatever bipartite graph. Or
it does, but part of the sophistication that comes with the formalism, hopefully I'll be able to present with when I get my notebooks and I get everything in order, will be that you can't forget about that they are. So for example, for things like walks, you want to remember that they are different because you want to. So basically, you can only walk between actual places, which are the vertex places. But if you're thinking about vectors as fields of directions, where you want to do vector fields or something like that, then you can actually think of the induced graph between vertices and edges in a very homogeneous way, and you basically just rewrite and do partial operations like in this rewriting hypergraph philosophy in a very homogeneous way. So, but you are only operating at the level of directed edges, and so this tangent graph level instead of the actual spatial graph. And I think by generating this tower, so this is what is very analogous to actual differential geometries, that you begin with a space. In the differential geometry case, that's a manifold. In our case, it's a graph, hypergraph. And then you generate these bundles in a differential geometry case, tangent bundle, cotangent bundle, tensor bundles, and whatnot. In our case, what you generate is this more refined hypergraphs that effectively have these edge places. And so you can construct similar graph theoretic or hypergraph theoretic methods on top of those that will basically tell you things about the spatial hypergraph that you began with, but they are technically new hypergraphs that live on top, right? So in that sense, it's very beautiful because we actually have a very direct analogy between differential geometry and this sort of infrageometry, hypergraph geometry kind of perspective. And it's just a matter of really fleshing out the definitions and actually making it computational, because in the end, these are going to be functions that you operate, rewrite rules that you partially apply, and so you have everything working partially and only in the regimes where they are defined and so on. But because it's a rewrite system, we're all good. And so yeah, it's working quite nicely that way.
Well, I mean, but one point here is that presumably there are things you can formulate purely in terms of tangent bundles without, I mean, you could sort of, for some purposes, you can throw away the space and just look at the tangent bundle.
In what sense?
Well, I don't know. I mean, in maybe I need to understand more about the traditional formalism of differential geometry, but I would think that there are things for which there are computations that you can do about, I don't know, some topological property of the space.
Right. Yes. So exactly. So for example, a very good example of what you're describing, I think, is the kind of algebra that you get on sections of the tangent bundle, vector fields, right? So they have a calculus of their own.
Yes.
So the analogy here, I'm quite excited because the analogy here is actually you have to take seriously this approach of rewriting hypergraphs that, I mean, it's kind of very ongoing in this whole physics project. And you have to take this philosophy seriously and say, okay, in the differential geometry setting, I had to work hard so that I have well-defined operations. So I have addition of vector fields or composition of vector fields or Lie bracket of vector fields, and these things, you have to kind of work hard for them to be well-defined. In our context, as long as the notion makes sense in a local sense, meaning, you compose vector fields, as we said last time, by concatenating them and basically doing composition of paths, but locally, then composition of vector fields reduces to a simple single rewriting rule for your graphs. And so vector fields are just assignments of directed graphs, or in some sense directed subgraphs of that sort of place graph, edge place graph. And then what you do is you apply this rewrite rule in typical rewriting fashion. So it's multi-way, and you have this sort of subtlety, but it works because I mean that's the it's no globally defined. You don't have an actual algebra in the conventional sense, but in our formalism we work with it because it's based on it's captured by a rewrite rule. And whenever you have several objects that are vector fields defined on your graph, you can just apply the rewrite rule and it will act partially and in only the places that it's defined. And it will give you a new object of the same kind because the rewritten graph will be a new vector field graph. And so you have a sense of closeness, the algebraic closeness, that is not based on the fact that you have actual operations, but still you are computationally sort of closed, right? So, yeah.
Although I don't understand the multi-wayness and how that comes in.
So this is what I hopefully will illustrate when I get hold of my notebook. But basically you are replacing here. So in order to claim that you have something like an algebra of vector fields, like we discussed last time with addition and composition, you are replacing the notion of composing two vector fields with the notion of composition is a rewrite rule that is going to pattern match for the occurrence of, for example, vector field X having a directed edge that has a head at the tail of vector field Y, right? Yep. And every time that you spot that pattern, you're going to rewrite for an edge Z that has.
I understand.
Right. So that's why you turn into this rewriting philosophy. And the beauty of it is that because we have this computationally implemented, you are de facto, and everything is finite, you are de facto defining something like an operation algebraically, meaning if I give you a vector field as an assignment of directed edges and another vector field as an assignment of directed edges, and you apply the rewrite rule, it's going to apply in all kinds of ways, but the finalized process, so it is a multi-way in terms of the application, but if you keep on applying it and you just keep the rewrites, the actual outputs of the rewrites locally, the final result of that is a single well-defined vector field. And so that's and there's the subtlety of when that is actually always happening or not, and that's kind of a subtlety that you have to grapple with. But generally speaking, you can define this as an operation without it being mathematically an operation because it's finite and it's computational.
Yeah, right. And it has some confluence property, presumably that is what leads it to be not to matter in which order you apply these rewrites somehow.
Yes. So that's the subtle part. We have to be careful because you might need to define something like what I normally call the one-pass rewrite, which is essentially taking an empty graph and filling it in with the outputs of the rewrites, which is how you, for example, recover matrix multiplication from a graph composition. But up to some subtleties, essentially, yes, you are relying on some confluence properties so that you actually have this well-defined.
All right, let's see. Jonathan had, and by the way, I need to remind myself, I mean, the addition of vector fields is simply, you just add up the values, right?
That's complicated. Addition is actually, I don't understand it yet. I don't think.
Well, I mean, given two identical graphs, if you've got two different fields, two scalar fields, okay, addition of scalar fields is straightforward.
Yeah, scalar fields, yes. Scalar field addition is easy, yes.
Right. Now, in the case of your places, edges as places, where you're sort of reifying the vector field, yeah, it is a little bit unobvious how that would work.
Yeah.
But Stephen, sorry, the question you asked at the beginning about surely there are things you can do by just looking at the tangent space structure. That's kind of what Riemannian geometry is, right? The whole idea of Riemannian geometry is that you have this inner product structure on your tangent space that varies smoothly, and as long if you only know that, you kind of know everything there is to know about the manifold. Which is another way of saying if you only know about the tangent space structure and you know nothing else, there's nothing else you can sort of infer.
Walk me through what that. Okay, so I mean,
so the case that you're referring to in our context is that's precisely the case where one of these graphs is equipped with whatever the discrete analog of Riemannian structure is.
Okay, but you're saying that it is not true of every graph, that you can throw away the underlying graph and just keep the tangent.
Well, we don't know, I think. It's certainly not true of every space. Not every space has a, is Riemannian. It seems plausible to me that every graph has a Riemannian, just like graphs are all, door spaces. It seems plausible that they're also all Riemannian. But I don't think we have a proof of that.
Yeah.
Okay, but so hold on. First thing about graphs, and we should write down some of these things. There are no discontinuous functions on graphs, is the claim.
I'll put that over here.
Yeah. Once you take this edges as places approach.
Any functions, yeah, of varying degrees of smoothness.
Yes.
Yeah.
Okay, so now what would it mean in a trivial case like that grid graph, my favorite kind of grid graph thing? What would it mean for that to have a quotes Riemannian structure when it's been labeled?
Yes. Well, okay. You wouldn't label it, right? I mean, Riemannian structure is something that belongs to a manifold, not to a function on the manifold. So what you would do is you would say, okay, so if I only know the information about the tangent spaces and how they kind of plug together, which is really what the metric tensor is, all of that information is somehow summed up in the Riemannian metric.
Mm-hmm.
If that somehow tells you everything there is to know about the geometry of this graph, then it's Riemannian.
Okay, but how do you construct this? The construction that you previously described for the tangent. Let's see.
Yeah, so that would, in other words, that's saying, if you like, if I only know the outgoing dangling edges from each vertex, is that enough? Is that information enough to construct everything I might care about in relation to this graph? I think the answer is almost certainly yes, right?
But when it dangles, does it know where it connects?
Yes. So I mean, it would know its limit points.
Okay, fine. So if we labeled every node here, just trivially, just vertex label our automatic in that thing. I don't think you don't need it. You can just put it inside the grid graph.
I know.
Okay. All right. So we've labeled it. Okay. So now every dangler, there's a 6-5 dangler, there's a 6-7 dangler. And if all you have is a bag of danglers, you can clearly reconstruct this graph from a bag of danglers.
Right. But again, there's an important subtlety here, right? So if hang on, let me reuse my code from up here. No, where was it? Down here. Whatever.
You need the edge coordinates.
I know. But okay, if I just take this example, right? So you have a bunch of arrows that are pointing to these, to these interstitial points between the vertices. Yep. The connection is then the rule that tells you precisely what is the endpoint. In other words, the connection is the thing that tells you, if I follow this tangent vector, where do I go? So all this is saying is, if I define, so the statement we're making up here is almost a trivial statement, which is that if I define if I introduce a metric compatible, a connection that's metric compatible, then I get a Riemannian manifold, right. Which is a tautological statement.
Okay, but hold on. So I'd like to write down the statement that the connection is the establishment of dangling edges.
So yeah. Well, claim. Connection is the rule that that sort of tells you the end the terminating vertex of a dangling edge.
Okay, but so normally, so in the normal world of connections and so on, let's see, what is the okay, let's look at a covariant derivative for 1 second. Okay. So we can define a derivative. I mean, we can define of the scalar field, there's perfectly reasonable derivatives to be gotten.
Right.
Do you agree in this? They're just how the field changes from one node to another.
Yep.
the so now walk me through how the covariant derivative works in the presence of this connection.
Well, so what you need is, and okay, so I don't know, I don't have an answer to this question. I don't think Carlos does either.
Can I jump in for a second?
Yeah, please. But
so actually, the notion of a metric is not entirely obvious yet, I don't think. So our initial guess back when we were not thinking of edges as places, but it applies here, I think, very directly, is that you want to take the infinitesimal notion of metric, meaning the tangent sort of quadratic form notion of metric. So you want to somehow so basically a notion of angle. So if you take two vectors defined in this way, and you want to assign some kind of scalar value to them, the only information that you have to get going is the incidence structure of your graph, right? So you can define some kind of discrete or sort of Boolean valued or maybe finite field valued angle simply by doing some incidence condition. For example, last time we said if the vectors are pointing to edges that are incident, then that's it. If they're pointing to edges that have adjacent vertex elements, then you say that the angle is 0, and otherwise you say it's 1 or something like that. I think yes, we have that somewhere in that notebook.
Yeah. So this is our rank 2 angle tensor.
Yeah.
In that case. So
that definition still applies in this context. In fact, it applies in a more tidy way because you have the edge that is sort of highlighted. They are a different kind, and so defining this metric structure is not entirely obvious at this point, and so the other angle is the distance function, right? It's having some kind of distance function that is assigned, but now you have to think that it's assigned to paths, to some notion of a curve in your space, right? And so because the norm of a vector doesn't really make a lot of sense in our context. So in the sense of distance of paths, we do have an
sorry, what is a vector?
A vector. Okay, so a vector is in the current definition is a directed edge of the edge place induced graph. So the graph that you induced with the red dots. So it's a blue to red.
That's like a tangent vector, but I mean, there's also a whole path made of many of those things.
Yes, exactly. So that's where the sort of subtlety comes in, that you have paths on the tangent vector. Let me call this red dotted graph the tangent graph for short. That graph. So you have walks on that graph.
Yep.
And they may or may not correspond to actual paths on your spatial manifold. So that's the spatial graph. That's the notion of integration, right? In the sense of vector fields. So you have some distribution of tangent directions in a space, and the question is there a curve such that its tangent matches that field of directions, right?
Yes.
So in our context, that is expressed as I give you a walk on this tangent graph, and the question is, does it correspond to some path on what I'm calling a path, which is a non-overlapping walk on the spatial graph? And obviously, there are many walks on this tangent graph that do not correspond to those, in particular, those that connect red dots, right? The red nodes cannot be connected because you always have to walk through an actual point of space, an actual vertex, right? So, but also not all the paths that connect the vertices are actual spatial paths because they might not be connected by some edge, right? So, so this notion of integration is going to be closely connected to the notion of connection, and then if you have a way of saying how your tangent paths or your tangent walks on this graph correspond to actual paths on the spatial graph, then you might be implementing. You might have the notion of or the possibility to implement the notion of a metric as the relation between the scalar, pairwise scalar relations of vectors and the scalar assignment to the distance of a path, right? As in usual Riemannian geometry, where you have, a metric tensor allows you to define a geodesic distance measure. So, but at the moment, it is not entirely clear how to give the sort of like full stop definition of a metric tensor, because there seem to be several options here. My canonical choice is that you look at the incidence structure of where the arrows are pointing, right? And you see whether there are intermediary, or maybe the shortest path between intermediary that could be an integer valued angle, right? To basically count the number of edges that you have to go through in the shortest path between the edge places that you are pointing at, right? But it's not clear yet entirely how to make the definition, because there seems to be choices and it's not obvious which one to go.
Right.
I think that if I were to, so what I'm focusing at the moment on is that it's trying to recover this Lie algebra story that we mentioned at some point, because we were running into issues, and I think that this edges places is going to effectively give us a very analogous story to the differential geometry one, because it effectively recovers all the algebra for free, because we now have actual tangent spaces as separate to the underlying intrinsic space, and we have the notion of, for example, the directed edges going into a vertex node is that's the negative vector, basically. The positive vectors are the ones outwards,
Yep.
and the negative ones are the ones inwards. And you can think that the actual tangent space is the collection of all of those, right? Both inwards and outwards. And so you basically have you mentioned in the last live stream that you said, oh, it would be great if differential geometry was explained like that. This is exactly what we're doing. We're basically having a discrete analog of the differential geometry. And what's great is that we're actually developing it by necessity and not by pictorial analogy. So it's nice confluence there.
Yes. What's Jonathan up to here?
I'm plotting a vector field. Sorry, ignore me.
Can I jump in for 1 second?
Sure.
So Carlos, you said you'll recover the algebra. So if I'm interpreting it correctly,
I think he means Lie brackets and things, not. Go ahead. What were you? I mean, I don't even know. What is the relationship? Okay. Yes. Go ahead.
So it's like in differential geometry, like you can take the Lie bracket, it forms Lie algebra. So in here, like when we didn't think of edges as places, and we just thought of the endpoint as just we just thought of as a vector from pointing from one node to the other. We do not get a Lie algebra structure, and the weighted derivation story that we introduced, that was like we got an extra term that caused it to have.
I remember you were talking about that last time. Yes.
Yes. So in here, since we are introducing like these midpoints as like these extra places which are in between the edges, if I have a function at a node, so the function over there would be like something plus epsilon, like a small perturbation. And since epsilon squared is 0, you would recover the Lie algebra structure. Is that what you were going for, Carlos?
So what I'm suggesting is, yes, morally that you are going, that now we have a notion of infinitesimal displacement. Before we only had whole displacement, and that's why we talked about discrete difference operators and so on, or finite difference operators. Now there is a way, it's still discrete, still graph based, but there's a way to tell apart a whole displacement, which is vertex to vertex, or potentially an infinitesimal displacement, which is vertex to edge place, right? Yeah. So that's exactly right. We now have a discrete handle, a graph theoretic handle on what it means to be near something, but not quite there, which is being.
That makes sense.
Yeah, exactly. Yeah.
Okay, so this is a vector field, except I don't know the red dot. Oh, I see. The confusion here. You should make different colors. The vector field. There's got to be a color of vector fields, purple or something.
So, Jonathan, in fact, you need also red dots to have outgoing vectors.
Okay.
Yeah.
By the
So
way,
in that,
purple is a bad. Let's make it. I don't know, blue or something. Purple is bad because we can barely see it. Okay,
is that any better?
not really, but it's not terrible.
Okay, well, no. So in that case, then we can just.
But the only constraint is that you don't connect red to red, but otherwise it's a general choice of edges.
Well, in that case, we can just do that, I think.
Yep.
Yeah. So I think the important point is that a path that terminates. So we have vertex points and we have vertex places and we have edge places, so to speak.
Yep.
And a graph path that terminates at vertex places is the analog of a curve, and and one that terminates that has one end at a vertex place and one end at an edge place is something akin to an infinitesimal vector, right?
Yeah, I'm calling them traces to distinguish.
Right.
And what about a red to red? What about
I don't think those are allowed, are they?
Those are not allowed in principle. I think we might have interpretations for those down the line, but at the moment, because those could be something like higher order displacement or higher order derivatives. We are thinking of this as tangents, but at the moment, I think they're just not allowed for the first order interpretation of tangent space. Yeah.
I mean, one thing that I think I brought up in the last Institute live stream that we did, which I think would be kind of cool to look at, is to see whether this interpretation of these edge places as, sort of the analog of infinitesimals, whether we can make that algebraically precise. Like, in other words, whether we can recover the axioms of something like, non-standard analysis by looking at essentially the algebra of how these infinitesimal distances compose.
I'd recommend doing that for this one-dimensional grid graph.
Yeah.
I think that would be a straightforward case.
Right.
Because that's like the one-dimensional.
At the very least, it's easy to see how fairly simple axioms like, epsilon squared equals 0 should be true. But the question of whether the full algebra of infinitesimals can be recovered.
Why is epsilon squared equals 0 true? Because you can't go there's only one red dot between two.
Yeah, exactly. You can't subdivide. You can subdivide this distance, but you can't subdivide this distance, right? Exactly. So you can see that there's the beginnings of an algebra of infinitesimals, but I think we don't yet know what it is.
That sounds like an UTI project to me, to look at the one-dimensional case and try and see what the algebraic version of that is.
Yeah.
Sure.
I think, Jonathan, I think just as a comment, are we actually expecting to get an algebra of infinitesimals? I think we probably can only content ourselves with the discrete analog of that, which is going to have something like that, a finite element extended algebra, right?
Right. I mean, it would be very surprising if we got exactly non-standard analysis, but understanding where they differ would be kind of cool.
No, I mean, this is discrete non-standard analysis somehow.
Yeah,
and
that's right.
What the heck is that? Because the general topic here is discrete analysis, whatever that means.
Yes, that's right.
Which is unfortunately already a term that does not mean this.
What does it mean?
Infra analysis, right?
What's that? Yeah, it's got to be infra analysis. But what does discrete analysis mean?
Discrete analysis normally, like, there's a journal called Discrete Analysis, which mostly, for instance, publishes results in things like extremal combinatorics, which is related.
Oh my God! But it's not even. It's not like finite. It's not like recurrence relations and so on.
No. But it's more like, for instance, Banach geometry, right? Cases where you're doing something, you're sort of investigating a functional analytic problem, but you're doing so using some kind of combinatorial structure, like
Mm-hmm.
Yeah.
Fair enough.
Which is not quite the same.
Okay.
But so one thing that's important to just mention before we forget it is, so obviously we've been talking a lot about the arity 2 case. But so here, wait, no, actually, let me show where was the one where I had an interpolation? There we go. So here, where we say, okay, we're assigning values of the function, not just to the vertices, but also to the edges. There's no particular reason to just privilege, arity 2 edges. And so in particular, if you take, say, this path here from this vertex to this vertex to this vertex, it also makes sense, to ask, okay, given these 3 points on the boundary of this polygon, in this, more generally on the boundary of this polytope, what possible value could be assigned to the interior, right? And so in general, for any length path, we want to be able to assign a value to that path,
Yes.
not just to the RT2 edges. And so that led to us. I don't know. I don't know if we came up, or if Carlos or anyone came up with a more sensible name. But we then, in the last live stream, started talking about what we provisionally called hypergraphs, a kind of generalized transitive closure operation where you take, in this case, an underlying RT2 graph, and you look at all of its paths, and you introduce, all of its length n paths, and you introduce an arity n hyperedge for each such path.
Right.
So in this case, okay, if we take this graph, so I guess we could do graph, say text list.
So these would just be basically like the path groupoid of the.
By the way, I mean, an interesting point about graphs is if you're just given the graph, you don't have the topology of, you don't have which edges bound a face. But what you're doing here is you're saying, actually, for any set of edges, they can bound a hyperedge, right? So in the traditional way of saying, how do we construct an ordinary topology from a graph? It's not obvious, because you have to, if you've got a triangulation of something, for example, then it's pretty clear how you construct, set up topology, construct all kinds of things. So what you're doing here, which is rather interesting, is you're saying, instead of asking to get faces which have immediate geometry, get hyperedges, which are somehow combinatorial kinds of things.
Yeah.
Make any sense?
So yes, and I can maybe expand on that intuition. So the reason to include hyperedges, I think, can be quite intuitively argued. Basically, you in this edges as places philosophy, you want to think that if you have 2 vertices in the binary case, you say there's 2 places, 2 landmarks in my landscape that I can look at, and then to say that there's an edge between them is to say that there is some place between them, right? There's something you have to traverse in order to travel from one to the other. So if you consider 3 landmarks, ABC, whatever, to say that there is a ternary edge between them is basically to say that there's some space between the 3 of them, and so that information is logically different from saying that that there is some space between any of the pairs, right?
Sure.
So that's why you can kind of self-justify that. Okay. Yeah.
Okay, but I'm trying to understand the analog of a vector field as this tangent, the concept of a tangent vector becomes something more general. A tangent, I don't know what the heck it is.
Yes. So yeah, exactly. So this is exactly what people in the case of in the directed case, where you make everything directed, you will be defining what people would call blades or multivectors in sort of geometric algebra language. So these are the sections of the higher antisymmetric powers of the tangent bundle. So these are very well known in differential geometry, and in this context, you will be thinking exactly as what you say, which are hyperedges, which are made up of 1 vertex point and several edge points, right?
Yes.
Yeah.
Yes. But I mean, wait a second. 1 vertex. Oh, I see. You're one of the vertices, and
so maybe it's easiest to think about it in terms of the limit construction from before, right? So when you just had binary edges, what you're saying is, okay, I've got a vertex place and I have an edge place, and that determines the limit point, which is the terminating vertex place.
Yep.
But in the RT3 case, you've got a vertex place and an edge place, but that determines 2 further vertex places, right? Yep. And so if you constructed a bundle here, it would be, and you take a global of these objects and you take a global section, you're not going to get a vector field. You're going to get something that's more akin to a rank 2 tensor field.
Yeah.
And how does that relate? I mean, I have never understood this geometric algebra business. And, there are a whole bunch of people who have kind of militated, I suppose. There are geometric algebra activists who've said, we should pay attention to geometric algebra for purposes of what we implement in Wolfram language and so on. And I've never understood what was being said there.
I think just as a comment, it's a bit tangential, I mean, pun not intended, is that the geometric algebra business is mostly relevant for actual Euclidean geometry or Riemannian geometry. In this discrete context where we are trying to first emulate general differential geometry, the geometric algebra perspective, I don't think is necessarily relevant immediately. Because I think what geometric algebra does is it condenses in a very nice algebraic package the notion that the fact that you have an inner product in your vector space induces all forms of area forms as well, the determinant and all the sub-determinants and so on.
I see.
So it's a nice package, a nice algebraic package to have a geometry encoded in algebra kind of thing. But in this context, I don't think it's particularly relevant. It's just that we are recovering the objects that geometric algebra speaks of, which is this set of vectors into a higher order, higher rank object called a multivector, a blade, and in this context, it's just very clear that the arity of the edge is maybe -1, the dimension of or the order or rank of the multivector or tensor that you're representing.
So can we talk about vectors versus one forms and things? I mean, is there a relationship here?
That's interesting.
Go ahead.
That's interesting. Yes. So taking the definition of one forms as the dual of vectors, then you're essentially looking at functions over the graph of this thing I'm calling tangent graph, and essentially we should probably prove at some point. I didn't have time to go over this cotangent construction, but we should prove at one time that the information of what we should encode as a linear mapping of tangent vectors is actually also a directed edge of some other graph, and prove that they are isomorphic. Actually, that might be one of the cool exercises to do in a finitary case, in an actual computational example, to show that we are on the right track, that we can recover the fact that the cotangent bundle and the tangent bundle are perhaps non-canonically, but isomorphic, right? That they are the same dimension. This is something that might be actually interesting. But
so this is one of the reasons why in the original plotting of this picture, why I didn't include directed edges coming from the edge places, because so this may be extreme. This may be completely wrong, maybe overly naive. But my intuition behind all of this has been that the edges that go from an edge place back to a vertex, those are the analogs of your covectors or your one forms. Because so then so if I traverse from here to here and then back again, I get back to where I started from. In other words, I get a scalar. Which is another way of saying that if I multiply a vector by a covector, I get a scalar.
Why do you get a scalar?
Because you get a value.
I get a value at that point, right?
But why? Where is the value coming from? You only have the data of two directed edges, right?
But
I'm imagining a Boolean function, for example, that if you specify at a given vertex point, right? If you specify one incoming direction, you can just match against all the outgoing directions and say, are you closing the path or not? And that's a Boolean function, right?
Right.
So that actually I like it. That's an actual possibility, but it's actually a function, because that's the thing. A dual vector is a linear function on all the tangent vectors, right?
Right.
So that's a possibility.
Right. Yeah. So our underlying field is always F2 somehow.
For example, yeah. I mean, I guess, yeah. That's interesting actually. I was thinking of the incoming vectors as negative vectors, because that's kind of what negative means also in geometry, right?
I would say that okay, I don't know. This is we're resorting to battle of the intuitions here, which is I can't justify any of this, right? But I would have thought that a negative vector would. So if you have a vector going from this point to this point, the negative vector would be the vector going from that point to that point. The covector would be the vector going from that point to that point.
That's what I would think too.
Yeah, that's also, yeah, that's right. That's right.
Can we write down that guess?
Okay.
And
yes.
then I want to understand
vectors take you from
vertices
to edge places. Covectors take you from edge places to vertex places.
Okay, so can you explain to me what a p-form?
Yeah, so I was just going to comment that I don't want to seem too down on geometric algebra, but my view is that it's just, I don't know, Carlos, correct me if I'm doing a grave disservice, but I've always kind of viewed geometric algebra as just a way to get geometric intuition for some kinds of tensor products. So the idea is, okay, if I have these two, so let's say I take these two vectors, I can compute their exterior product, which gives me a two-blade, which in this case is going to have the interpretation of this triangle, which I can represent as an arity 3 hyperedge, as Carlos said, and that just gives me and then there's a vector space of those arity 3 hyperedges of those two blades, and then I can take products of those and so on. So I get this whole infinite hierarchy, and so it's just a way of geometrically visualizing and reasoning about what it means to take tensor products of tangent vectors or tensor products of higher rank objects.
Well, that together with a notion of dot product, right?
Right.
So you have those notions, and then the moment you throw in a dot product at the sort of vector level, then everything, the Clifford algebra gymnastics sort of closes everything into a nice fold, and you have the geometric algebra. But yes, it's a good characterization. I never saw it as anything particularly revolutionary or breakthrough. It's more of a nice package of known structure.
Okay, can we talk about exterior calculus and how we get we said a one form is associated with going from an edge place to a vertex place. What's the two form?
Yeah.
So in that, so modulo this guess, right? Then a two form. Okay, so if you take this is like our two blade. It's or I can equivalently think of it as being the tensor product of two tangent vectors. The
dots there are vertices. Is that right?
The dots here are vertices, exactly. So this is
vertex places.
Okay. Vertex places, and then this is a single edge place, but it's a three edge place.
Yep.
And so I can consider a path going from any, so if this were embedded in some larger hypergraph,
you think a two form is basically just the going out from that, whatever is in the middle of that, whatever is the red dot.
Exactly, it's the thing that's going from this hyperedge to the vertices, whereas the rank
nice.
2, exactly.
Tensor, right, is the ordinary rank 2 tensor as opposed to the two form is going the other way somehow.
Yeah, the rank 2, the contravariant, is that right? Yeah, the contravariant rank 2 tensor is the thing going from the vertices to that edge. The covariant rank 2 tensor, i.e. the two form, is the thing going from the edge to the vertices.
Okay, so now let's do the next exercise. Can we write down this point? I mean, I like this idea that you erect to get a P form, a rank P tensor is just a bunch of P dangling edges going out from a given vertex, is it not?
Yeah. So I'm gonna be a little bit. So I'm not sure if we should settle exactly on that. I do like the definition because it's concise, but
let's take this as hypothesis, Carlos. I'm not sure it's right either, but okay. The contravariant case is
I'm not sure it's right either, but
I do have a comment that maybe I'm not saying we shouldn't try this definition, but the comment is if we are thinking of a spatial hypergraph, the data of a spatial hypergraph, which is going to have a mixture of order of arities of edges, if we're thinking of that as this is our primary spatial data, right? And we are thinking that so we're basically saying only arity2 is going to be the tangent vector, right? So the tangent vector sort of data. If I want to traverse an edge place that happens to live in one of these arity3 or higher arity edges, then I will never pick that up in the sense of paths, because I'm not considering them for tangencies, right? So that's why I like the conciseness that just arity of the edge determines the order of the form or the order of the tensor. But I think we might be going a little bit against the base philosophy of the hypergraph is the spatial data, and then it's our parsing of the hypergraph how we get all these higher forms of algebra and sort of tensors and so on.
Okay, but I still want to, in this theory that the higher hyperedges, the what we can say
because so I can defend what I'm saying by the following. So imagine, so you have a random hypergraph, like the graph that we drew, but with higher order edges in between. You draw the red dots in between edges regardless of their arity. Then you can generate the same way that we generated a directed graph out of those to define tangent vectors and so on. You can generate higher order hypergraphs in the same way, right? Where you're basing your vertex points as different as the edge points, and you're generating hyperedges, this sort of tangent hyperedges and higher tangent hyperedges, this multi-tangent hyperedges, and then you generate this higher hypergraphs, right? So it's not that you generate all possible hypergraphs that way, but you are also constrained, but you're somehow mixing the orders of the edges, and you're just counting the number of them. So basically and this is actually what we want, because we want to have the number, so the order of the hyperedge that you can create out of a vertex place is the maximum number of the maximum arity of that edge is the degree of that vertex place. So that's exactly matching the intuition that the dimension of your space is directly related to the degree of the hypergraph, right?
Well, okay, but hold on. This is exactly what I was going to ask. I was going to ask about Hodge star operations and so on, and I was going to dual operations,
right?
Because there's a point at which you've kind of, the local saturation of edges is different from the global saturation of edges. The global saturation of edges is what gives a global sense of dimension. The local saturation of edges, you can have a 5-dimensional object where every local vertex has just three nearest neighbors, so to speak.
Yeah.
So I'm trying to understand, in these interpretations, it should be the case that you can start seeing these membranes, you can start seeing sort of, as you try and globally construct these membranes, you should start seeing something that reveals, the dimension of the effective dimension of the space.
Yeah, and what I'm saying is that I agree, and what I'm saying is that it is not yet obvious to me that we should be thinking of the order of a given edge as an effective token for dimension, which is what we would do if we do this particular choice of edge placed into vertex place, a directed edge, to be the placeholder for a higher order tensor at the higher rank tensor.
Well, wait a second. There's two different things. There's the rank of a tensor and there's the dimension of a space, which are very different things.
Yes, but yes, they are different things. But the dimension of the rank of a tensor, the rank of a form, of a P form or a multivector, is cannot be higher. Higher than
exactly. But that's not true of a. Right. So in these P forms, what should happen is, as you try and construct, the point is that constructing it very locally, it's going to depend on the arity of edges and stuff like this.
Yeah. So I guess, okay, I can boil down the two options that we have as follows. We can either look at a vertex and then basically parse the edges by arity, and then that's going to give us a token for a dimension. Or we could look at a vertex and look at its degree, and then take that as a token for dimension. That's basically the two options I'm seeing here.
Okay, but I think we already have a definition of dimension that we like quite a bit, which involves creating bigger and bigger geodesic balls.
Yes, that definition is no, but that's kind of the estimate definition. That's why I said the placeholder for a token for dimension, which is like the infinitesimal dimension, the analog of the dimension of the tangent space at a point, which in differential geometry happens to match the global definition of the manifold, but in the discrete case it might be different, as you say,
Right. So what would happen is there's a local dimension that is 2, 3, 4, 1, 2, et cetera, et cetera, but which somehow averages out to the
or somehow
actual...
depends. Yes, I agree. Yes, yeah, exactly. But what I'm saying is that the local dimension, I'm seeing two choices. I don't have a particular preference for either, but I don't see a good reason to choose one over the other. Which is that you either take the arities of the edges that are incident in that vertex as the token for dimension, or you look at the degree of that vertex as a token for dimension. I don't have a good sense of which one should be.
I understand.
Yeah.
Cool, Jonathan. Well, okay.
So the claim would be that that's a two-form, right? A two-form at vertex A, vertex place A.
Yes. Yes.
Wouldn't that be a two-vector?
No, it's a two-form.
Wait. No, you're right.
Two-vector.
No, hang on.
Oh, you are right. Yes, that's a
you're
two-vector.
Right. Yes,
a two-form would come out from that node.
From the red, yeah.
Yeah, so that would be, hang on, let's get this right. Yeah, okay, no, so it would literally just be the reverse of this, right? Yeah, you're right. Okay, so then that's a two-form, that's a two-vector, and then you can even have a mixed index tensor, rank 2 tensor, which would be that case.
Yes. All right. Listen, are we at a reasonable stopping point? I'm supposed to go and do something else. Did we? I mean, this seems to me it's progressing, and there are obvious questions to ask here.
Mm-hmm. Carlos, Uti, were there other things that were figured out that we neglected to mention?
I don't think so. At least not without having the time to expand. That next time we can do. So I think it's a good stopping point here.
Okay. I mean, progress is being made here. It's when you build things up from such a low level, it takes a while to get.
It does.
I mean, it feels like the roadmap. There's okay. Just give me a little bit of a sense of the roadmap. We've got the notion of open sets and things. We've got just what's the roadmap? The notion of P forms and things seems to be coming.
Yes, and to me the most obvious thing is to try and have a computationally operational notion of tensor algebra of a manifold, so which is going to replace operations with rewrite rules and complete global operations with partially defined, partially matching patterns, but and so everything is going to live in this rewrite. So now that we have the spatial hypergraph that we are not going to rewrite, at least in this context of tensor algebra, but then you have all this tower of hypergraphs on top, this P-form, tangent hypergraphs. Those we are going to rewrite. We are going to be applying rewrite rules to and
Okay, so basically what we're trying to make is a compiler that goes from the operations of differential geometry to a bunch of graph rewrites.
Essentially, yes. That's to me that's one big goal, to have a nice correspondence. One column differential geometry, one column hypergraph rewriting, and be able to.
No, but I mean we can then operationalize differential geometry. This is a way. If we were doing numerical analysis, for example, we want to take differential geometry and we want to find some discrete approximation to it.
Sure.
This is a way in which we would say we are literally compiling this symbolically represented piece of differential geometry into this collection of graph rewritings.
Yeah, exactly. So I would say it's not hypergraph rewriting, it's graph rewriting,
Yeah,
right?
that's what I think too.
So
Yes.
because as Carlos mentioned, you've got those rewrites are not occurring on the underlying hypergraph; they're occurring on this kind of I think we were calling Carlos was calling it the tangent graph or whatever we're constructing on top of it. And so then it's I don't know, it's pretty clear that there things like index contractions you can just operationalize as if I contract along this index, that's adding another edge that takes me back here, so I reduce the rank of the tensor, and things
Yep.
and that's just a graph rewrite rule, right?
Yeah.
Right. So what I'm saying is every one of those things that can be described symbolically, and in many cases we already have symbolic descriptions in Wolfram language, we could write a compiler that turns that into
But that's
graph
the idea.
operations.
Yeah.
Yeah.
But so
that's the horizon for sure. Yeah.
okay, so where do we get next? When do we get to metric tensors? When do we get to curvatures? When do we get to I mean, we already think we know what those are, but it would be nice to be able to see that more rigorously.
I feel like there's a lot of scope for topology. The dangling edge construction was pretty nice, and the complement of open sets, like it really matched it nicely. So I'm kind of excited to explore like what do Hofstadter spaces look like, compact spaces, etc.
What do we say? So for example, things like
it would be
Euler
interesting
characteristics.
what the analog of the hierarchy of separation axioms would be.
I
Yeah,
don't know
exactly.
what those are. What is that?
Things like Hausdorff spaces, Tikhonov spaces, etc. Essentially asking like if you've got if you've got two open balls that are non-intersecting, do they always
Yes.
can you construct open sets that are that don't share limit points and things like that.
But what about all the results about sort of all the things analogous to Euler characteristics and Gauss's theorem and all this kind of thing? The relationship between vector fields and
right, but I mean, of course, that's we want to get there, but the problem is to make so with graphs, understanding what things like topological indices are is fairly straightforward. But you need to have a bunch of the underlying analysis machinery operational before you can really start making those kinds of claims, right?
No, I understand. But so getting the relationship between whatever the analog of the topological indices is for graphs, which I'm not sure is totally straightforward, but we can imagine it. I mean, I don't know, there's probably chromatic numberish type things that may be related to that. I'm not sure.
I mean, there's a fairly well-developed theory of graph homology that's quite sensible, right? General graph homology.
Okay.
But I think let me emphasize, because I think it's relevant here, that I do think that we're doing something that is slightly different from that, because if we are taking our base graphs as sort of the token for space, or this is what space should be in a discrete sense, then we're going to be analyzing graphs that are emergent from that in some sense, that as we described, these tangent graphs. So it might be that obviously we can pull techniques from graph homology and all these existing theories, but it might also be that we need to rely more on this sort of rewriting perspective, where our algebraic notions are now more graph rewriting notions, and we have to work more sort of native to this graph land than applying existing homology to that, or existing formalisms to that. It might be that there are interesting techniques there, but it feels to me, I mean, maybe I'm just too encultured now to thinking in terms of hypergraph rewriting, but it seems to me that if we're going to do something that is really proper to the name infrageometry or infracalculus, something that goes below, then we should do something that doesn't actually use existing formalism in an explicit sense, and maybe recover somehow. But there has this sort of infra engine, right, that is running in this sort of rewriting way, and we are just clever enough to spot the right patterns, and then we can say it's actually doing what we want, which is very similar to, I guess, what the physics project does with the generic graph rules, right?
Yeah.
So,
I guess the argument there would be that what you want is something that, just as the objective is to build something that operationalizes differential geometry and tensor algebra. We would be to have something that operationalizes effectively simplicial homology defined over one of these hypergraphs.
Yeah, exactly in a way that is purely graphical in some sense.
Yep. We're gonna get there. This is
So-
cool. I mean, it's and it will be very computational and operationalized.
Yep.
And you know, some results will be very straightforward, others will be complicated limits of what we're talking about.
Yep. Very likely.
Cool. All right. Well, thanks. We had some comments on live stream here, which I'm well, let's see.
Before we go, I mean, Jonathan and Carlos, when do we want to discuss the causality project? I have some interesting things to
Yeah,
discuss.
we should do that as an institute live stream, maybe next week.
Yep.
Okay.
All right. I got to go to something completely different, guys. Thanks a
All right.
lot.
All right. Thanks, everyone.
Okay. Bye-bye.